Right, welcome everybody. Today it's a pleasure to have Andreas Geiger here today with us. Andreas used to be a group leader at the MPI in Tübingen, and actually it's not so recent anymore. He's been a full professor in Tübingen now. He has received many awards. His research is very well known. He's a pioneer in computer vision and particularly 3D computer vision. His data sets, Kitty, are pretty much used in almost every computer vision algorithm, but also algorithmically, especially with like OCtNet and all of these kind of methods, he has made a tremendous impact in the computer vision community. So today we are really very happy to have him. And yeah, let's see what you're going to talk about.
Thanks, Matthias. Thanks for the introduction and thanks for having me. So I wanted to share some of our work from the last 1 or 1.5 years on neural implicit representations for 3D vision. So in general, the goal of our research group is to make intelligent systems more autonomous, robust, and safe. And we have a couple of projects that go into different directions. And one of them is into the direction of 3D vision. If an intelligent systems need to interact with a 3D world, it needs to get a pretty good understanding of the 3D geometry surrounding it. So I hope this video plays well. So it needs to estimate distances, predict affordances, or grasping points, etc. And this is true, of course, for indoor household robots as well as for outdoor robots like self-driving cars. However, 3D reconstruction is actually still a hard problem, despite it reaches back to the 1960s, maybe, with this famous Bloxworth paper. So how does a traditional 3D reconstruction pipeline look like? Well, what you could do is you could input a set of images, so multi-view reconstruction. You estimate camera poses using bundle adjustment. Then you find dense correspondences, you create depth maps, and then you fuse these depth maps into a coherent reconstruction of the object or a bigger scene. All right. So this is classical multi-view reconstruction. However, humans are actually able to recognize 3D even from a single 2D image. If I show you this image from the previous scene, you can tell me precisely what would happen if you would move forward, or what the approximate distance to each object in the scene is, or which object is in front of which object. So a natural question to ask is, well, what can we do with a single 2D image? Can we learn also to infer 3D from a single 2D image, or at least from few images, in contrast to this classical multi-view paradigm where you have a lot of images? So one of the scenarios that we're going to consider throughout this talk is this one here. It's very simple. On the left, there is a 2D input image, and then there is a deep neural network that produces some 3D reconstruction of that object that is depicted in that image. And you can see that this is a complete reconstruction, so it also reconstructs the surfaces that are not visible here in this image. Okay, so the input representation to this problem is pretty clear, right? So it's a 2D image. You can use a 2D convolutional network for extracting features from that image. But what is actually a good output representation? What is a good output representation that works well with neural networks, that can be easily predicted by a neural network? People have looked at multiple output representations for 3D structures being predicted with a neural network. One of the earliest work is this one here from IROS 2015, where they considered voxels as an output representation. Voxels discretize the 3D space into a regular grid. Here on the right-hand side, you can see like a 2D cut and also a 3D version of this representation. They are easy to process with neural networks because they are basically just requiring a straightforward generalization of 2D convolutions to 3D. But however, they have cubic memory growth, which limits the resolution even if you use some sophisticated space partitioning like octrees. And they also introduce some Manhattan world bias. You need to define some arbitrary coordinate system that has nothing to do with your shape, but that aligns the voxels. Okay, another representation that people have looked at after that is point-based representations, in particular point sets. So this representation as an output to a neural network is discretizing the surface of the shape into a set of 3D points. However, as you can see, these points, of course, don't model connectivity or topology. And also existing approaches are pretty limited in the number of points, in the order of a few thousand. And then more recently, even people have tried to use what is very natural in computer graphics, meshes, as an output representation for neural networks. Meshes also discretize space. They discretize into vertices and faces, and therefore also limited in the number of vertices, or otherwise speaking, in terms of their granularity. And what is more with meshes, they are actually a very difficult representation to be predicted with a neural network, because they either require a class-specific template, like a human face or a human body that is deformed, or they are patch-based. So the neural network predicts a set of patches that are not necessarily watertight or lead to self-intersections, as with these results here from AtlasNet. So meshes are just very difficult to predict using neural networks. In our CVPR 2019 paper, we have thought, well, why do we actually need to use an explicit representation? Can't we just represent the surface implicitly, which doesn't require any discretization, in contrast to the previous output representations? It allows for modeling arbitrary topology and resolution, and has a comparably low memory footprint. It's also not restricted to any specific class or category, as these template-based mesh approaches. So what do I mean by implicit models? More specifically, I mean implicit neural representations. I don't mean implicit models that still store data in voxels like sign distance functions, but I mean models where the sign distance function itself is represented through the parameters of a neural network. So the key idea here is very simple. Instead of directly representing the 3D shape explicitly, instead, what we do is we consider the surface implicitly as the decision boundary of a nonlinear classifier. So here we have a classifier f theta, parameters theta, that predicts from a 3D location and a condition, that could be an image for which we want to predict a 3D structure, an occupancy probability that corresponds to that 3D location. So here's an example on the right, in 2D and in 3D. Let's look at this 3D example here on the bottom. You can see this bench here. The bench surface is the decision boundary of a nonlinear classifier that tries to separate the red points inside from the blue points outside. You can think of these red and blue points as training points where the classifier is trained to separate them. And the gray surface is the decision boundary that optimally separates blue from red, right? And this separation is learned conditioned on a particular input, like the image that we've seen in the beginning. I have to say, the field is advancing very quickly, and so many ideas, in particular simple ideas, as this one here, appear multiple times at the same conference, as was the case also for us. So at the same conference, there have been 2 other papers that essentially developed the same idea. What you can do instead of predicting the occupancy, you can also predict a sign distance value. It works the same way. We used occupancy because it worked well enough for us, and it gives rise to a simple loss function, which is just a simple classification loss. But SDFs have other nice properties, and it's in general a good idea to also predict SDFs. Okay, so how can we now train this network, occupancy network F theta? Well, because F theta is a classification network, is a classifier, we just use a standard classification loss, the binary cross entropy loss, BCE. So what we have here is a batch of 2048 3D points. K is the number of points. And over that batch, we try to minimize this classification loss BCE. So what we do is we try to make the output of this occupancy network F for a particular 3D point, and input condition, the Z here is the image, similar to or the same as the true occupancy for that 3D point. So here P and O are the supervised data points, right? So O is the supervision for P. We assume that we have a data set with ground truth for the occupancy of random 3D points in this case. What we can also do is this is a discriminative model. What we can also do is we can build a generative model. We call this a variational occupancy encoder. And it's basically just a VAE, which has a reconstruction loss. This is the same as before, but in addition has this KL loss and an encoder Q that encodes from a set of points. This is a set of predicted points PO, the latent code C, and minimizes the KL divergence between this distribution and a standard Gaussian distribution. Right, so it's a classical standard formulation of variational autoencoders. And in that way, we can use our model also for generating novel shapes, as you will see in a second. So what does this look like? Let's look at some results. So what we can see here on, well, one thing I forgot to say is that this function f theta that I've shown you before is a simple MLP. It's a simple multi-layer perceptron that predicts from a 3D point location, inside and outside, and conditions on this global appearance code that is extracted using a convolutional network. For instance, if we have a image as an input, conditions on that global appearance code using a conditional batch norm. Okay, so here are some results. Here we see the input image on the left. This is a 2D image, and then the result of some baselines here on the right. This is a mesh-based baseline. And this is the output of our method. Now, because our method does not directly produce a mesh, what we do here to produce these results is to adaptively query the occupancy network in the 3D space such that we adaptively narrow down where the surface is. That way, we basically can recover arbitrary topology because we have just an implicit representation, and we can relatively efficiently recover the mesh. Still, it takes more time than having directly extracted the mesh. So it takes about 1 second or so to extract that mesh by querying this classifier that we have trained. So here's a comparison to ground truth. What we can also do with this model is point cloud completion. So on the left, we have a sparse and noisy point cloud of an object, and a network that is tasked to predict a complete and noise-free output on the right for different representations, point-based and mesh-based representations. And here's the result of the occupancy network. So here, what we can also do is we can take a coarse voxelized input and produce a fine and more detailed mesh as an output. In this case, it's kind of a super resolution task. The left is the input and the right is the output. And so finally, I want to show you some results of this generative model. In particular, here we have trained a generative model on various object categories. All of them are actually here from ShapeNet. And you can see latent space traversals. So we take latent traversals in the latent space between some data points. And you can see how the model interpolates, generates novel shapes that are actually not part of the data set. Okay. So this already works quite well, at least at the object level, and we will see later how we can extend this to larger environments like rooms and entire buildings. But first, what we have learned about so far is only about the object shape. Now the question we can ask is, well, can we also learn something about the object appearance? And there's a very straightforward way to do this in the same manner as we have done for the shape. And we call this texture field. What we do here is we assume that we have a 3D model available that could be either a CAD model, or it could be a reconstruction that is predicted by an occupancy network. And we have also a 2D image of the object. And then we have this texture field here, T, with parameters theta that predict for each point in 3D space a color value. And we train this network such that it predicts for each of the surface points a color value such that it projects well into an image, into a rendering of this 3D model. Okay. So we have also supervision for this. So we assume that we have textured 3D models available that we can render into images, and we can minimize the reconstruction loss for this. So here is a more detailed overview over the architecture. As in the normal occupancy networks I've showed in the beginning, we have an encoder here that encodes, in this case, a 2D image into a global code C. Then we have a 3D shape. We extract also a shape code by simply sampling a point cloud from the surface of the shape and encoding that using a point net. So now we have this global appearance and shape code. And what we then do is we take 3D points. We compute these 3D points by simply rendering depth maps and unprojecting them into 3D. So we can query 3D points for every pixel in an image. So we have a 3D point that is the input to this texture field. In addition, we have as input here, or as condition, the appearance and the shape code. And for that point, the network is tasked to predict the color at that 3D point, at that projected 3D point. And it's fully supervised, so we can apply a reconstruction loss here. So we minimize the difference or the discrepancy between the predicted pixel color and the true image color at that pixel. We can also apply this model in a generative sense. For instance, we could remove the reconstruction loss here and add a discriminator to produce a gun-like model where we have an adversarial loss. And here in this case, we don't have a encoding of the appearance parameters, but we have just sampled these appearance parameters from a standard Gaussian distribution, of course. And we can also build a VAE-like model here. Now we add again the reconstruction loss, but we also add an encoder that takes this input, this image here, and also the shape code, and produces a distribution in latent space that's then compared to the standard Gaussian distribution and fed back into the decoder, which is in this case the texture field. So let's look at some results. The first thing we have looked at is the generalization or the representation power of this model. What we see here on the left is a textured model of a cat. And we see two reconstructions of that cat using either on the middle here, a implicit model, the texture field model, and a comparably, in terms of memory, comparably similar voxel-based model, where you can see that the texture-based model, the texture field model here, retains more detail, but still over-smooths some of the areas. So you can see there's more details here in the fur region. Yeah, so this was a simple overfitting experiment to one particular instance. Now let's look at some results where we predict these textures for 3D objects from a single image. So here we have the input to the image that is given as input to the texture field, and we have the ground truth shape that in this case is also given as input. What happens if you use a simple novel view synthesis baseline only from a single image? It produces very inconsistent results because it, of course, reasons in 2D. So it's a simple image-to-image translation baseline that we've used here. While if we do this reasoning in 3D space, it's consistent by default. So here's the result of the texture field regression. This is another example. The view synthesis baseline, which directly tries to apply in 2D the texture and the texture field. This is another example. Now, what we did in this experiment is to reconstruct texture from a real image. Before, these input images, these 2D images that we have given as inputted to the network were also rendered from the ShapeNet dataset. But in this case, we show that it also works for real images. So here we have a cut model that we want to texturize with the texture that corresponds to a real image. And that's not even the same car type here. So it doesn't really matter. It can generalize to different geometries. So we could put the same texture here also on an SUV, for instance. And so here what we did is now we put the occupancy network together with the texture field. So we have first the occupancy network predicting the geometry, and then we have the texture field that puts a texture onto the geometry. And this is the final result. And yeah, we can also use this model in a generative sense. So here we see some latent space interpolations. So we can see the appearance changing when we traverse the appearance space for a fixed geometry. Okay, so this texture field model was doing okay in representing the texture of the object, but it wasn't able to represent any view-dependent variations, right? If you have a specular surface, then of course, depending on the viewpoint and the light position, the color value that you observe, the radiance that you observe changes. So this was not possible with texture fields. And so we have extended this model now to capture also materials and lighting. In particular, we've extended this model to represent surface light fields or to predict surface light fields. So the setup is the following. The input is, again, a 2D image and a 3D geometry. So it's the same as for the texture fields. But now we have a different neural network that predicts a surface light field, which allows us to manipulate both the viewpoint and the illumination. So you can see here some examples that have been predicted from this input, where we have on this geometry added the materials such that if we change the light position, then also the appearance changes. So that you can see the shadow from the back of the chair here. And you can see different viewpoints here on the bottom. So how does this work? It's actually quite simple. So how does light transport work? It's the very well-known rendering equation that you see here on the top, which is basically integrating over the hemisphere, the incoming light and the reflectance, the bidirectional reflectance function. Now we don't do this. What we assume, first of all, is that we have only a single point light source, and that's also how we generate our data. We have only a single point light source, which makes this integral go away, of course. And then we only model the surface light field. So what we essentially just do is we model a function, also a neural network, that for a particular 3D point and a view direction and a light location predicts a color value. This is illustrated here on the bottom. You can see the 3D point, you can see the light location, you can see the view direction. And for these conditions, under these conditions, and of course, given the geometry and the appearance of the object through this 2D encoder of the image, this network predicts a color value. So here are some results. So the first thing I want to show you are single object experiments where we look at shadows. So you can see the results of the model on the left and the ground truth on the right. And you can see that it can capture shadows relatively precisely. It can also capture some of the specularities, for not all of them. There's some specularities that are lost. And what it can also do is it can model entire environment maps, right? Despite the model being trained only on single point light sources, we can then at inference time apply it by rendering one point light source for every pixel in the environment map. So in this case, we use this environment map here. This is what you see here on the right-hand side. Right, so we train with a single point light source, but we can apply this model with an environment map. Of course, this is not very fast because you need to apply this rendering step now many, many times. So you need to query the network many, many times. So here are some results for a single view appearance prediction. So here we have an input image on the left. We have the image-to-image translation baseline, which of course doesn't work very well on the right. Also, texture fields doesn't work very well with materials because it basically just averages out the material information. Here are the results of this model where you can see the highlights moving, for instance, here on the armrests. I hope this comes across in the Zoom. Okay. Let me see how time. Good. Yeah, so the next thing we looked at is objects in motion, right? So we have so far only investigated 3D static 3D shapes. So what about objects in motion? So looking at the 4D component, basically looking at the space and time domain. Now, unfortunately, generalizing this idea of implicit occupancy functions to 4D directly is hard. And the reason for this is the course of dimensionality. And I will show you some results in the following video, which will show that if you do this, you would get very impoverished results because the network is not powerful enough, at least given the amount of training data that we have, to represent complex motions due to the discontinuity of the shape over space and time. What we do instead is we use a 3D occupancy network. That's what we propose in this ICCB paper, to represent the shape at a particular time instance, let's say at time equals 0. That's what we know we can do, right? And then represent the motion by a temporally and spatially continuous vector field. Now, this vector field is a 4D vector field, but it's relatively smooth compared to the 4D reconstruction directly. And that's why it's easier to predict with a neural network. Now, the relationship between a 3D trajectory or a 3D location S and the velocity V is given by a simple differentiable ordinary differential equation, as shown here on the bottom. In other words, the location, the derivative of the location with respect to the time component is simply the velocity. So I get, I quickly need to turn off my my Gmail because it makes some noises here. Okay, I'm back. Good. So the relationship between the 3D trajectory S and the velocity is given by this ODE here. And now we need this ODE to connect space and time. So we need this ODE to connect this reconstruction at time 0 to other time steps. Right? So it's basically a model that can, at any continuous point in time, infer a reconstruction. So here's an illustration over this model. What we have is we have an input on which we condition. There could be a sequence of point clouds or a sequence of images. And from that, at time step 0, we use an occupancy network to predict the reconstruction at time step 0. And then we use a velocity field network, V theta, that predicts for every point in space and time a velocity vector, but that's a very smooth field. And what we can then do in order to train the network using a simple reconstruction loss is we can take, this is an observation here, for an observation at time tau, we can take a point inside or outside that object, right? So let's say this point is inside that object. We can take that point and warp it through this vector field by solving the ODE until that point arrives at time t equals 0. And warping through this vector field is a differentiable operation itself. Maybe you have also seen the NeRF's Best Paper Award on neural ODEs, which is basically doing the same thing. So we can warp differentiably this point through all the way through to time step equals 0, and then we can evaluate the occupancy network at time step equals 0 and see if that point is inside or outside. So what that means is with that observation, we can backpropagate gradients both to the occupancy network and to the velocity field to match the reconstruction at that particular point in time. And then we can do this for multiple points in time, and we'll obtain this occupancy reconstruction at time 0 and the velocity field that connects all the time steps. Okay. So let's look at some results. Maybe one thing that's interesting to note here is also that no correspondences are needed. we can include a correspondence loss, but we can also just use this reconstruction loss, and the model implicitly establishes correspondences across time. And you will see this by the consistency of the colored reconstruction. So the same color corresponds to the same location on the object, and you can see that these colors are very consistent over time. So let's look at some results now. So these are results for point cloud completion. In this case, we have a very sparse and noisy point cloud as an input. It's a sequence over time, and we encode this sequence using a standard point net where we concatenate the point cloud simply. It's a very simple encoder. And here on the right, you see the results of the standard naive 4D extension of the occupancy network, which leads to this impoverished results. This is a point set generation network, and this is the occupancy flow model. And here's a direct comparison left to right. Yeah, so it's of course, if you ask people in the graphics domain, it's not, these results are not great, but also the inputs are very sparse and noisy, right? And yeah, one thing that is also not straightforward is how to extend these models to longer sequences. These are all pretty short sequences that we're able to do with these models. One problem, of course, with these models is also that you need training data, and getting huge amounts of training data of non-rigid objects in motion with watertight ground truth is really not easy. And that was one of the motivations that led us to the next question that I want to talk about is, well, can we also learn these implicit representations from images alone? So far, all of the results that I've shown have assumed that full 3D supervision is available, but can we learn these representations from images alone? And there have been some great strides on learning neural 3D representations for voxel-based and mesh-based outputs using differentiable mesh rendering, for instance. So the question is, well, can we apply similar ideas here to the problem of implicit representations? The nice thing about this is that the model architecture actually simplifies. Now we can use, and we must use, one model that encodes both the shape and the color or material of the object. So what does the architecture look like? It's very simple. Here we have again a 2D image that's encoded using a convnet into a global latent code. That's maybe a 128-dimensional latent code. Then we have a set of points. For all of these approaches that I've showed you before, it's most efficient if you input multiple points at the same time to the network, because as long as you have still memory left on your GPU, you can process all of them in parallel. So we have these 3 coordinate dimensions here for the input, and then we have the number of points on the other axis of this input. And then we input this to these 5 ResNet blocks. That's very similar to the occupancy network. But in contrast to the occupancy network that only predicts occupancy, here we have a shallow head now for the occupancy that for each of these like 2000 points or so here predicts the occupancy probability. In addition, we have a shallow head that for each of these 2000 points here predicts a RGB color value. That's why we have 3 outputs here. Right? So they share the same backbone, but then we have these shallow heads. Now the question, of course, is how can we render and how can we train? So for rendering, this is basically the forward pass in the neural network. And then we need to also implement the backward pass to backpropagate the gradient through this implicit representation and through the rendering process. So let's first talk about rendering. It's basically differentiable volumetric rendering. So here we are talking about the volumetric rendering part. So how can we render such a representation, as I've shown on the previous architecture slide, into an image? Here we see an image plane. We have the camera center. We have a ray W that connects the camera center and a particular pixel U for which we want to retrieve the color. And what I've shown here in gray is a visualization of the occupancy network where this thick line represents the surface. This is basically the level set where we assume the threshold maybe is 0.5, where we decide between inside and outside, right? So this is basically the surface. So what we can do now is we can find the surface point, P hat here, this point, along the ray W via ray marching and route finding. So we go in equidistant steps until we find this sign to change. So we, from smaller than the threshold, we go to bigger than the threshold. So we know that we have changed from outside to inside. And then we can apply the second method to very efficiently retrieve very precisely the surface point p hat. Then we can evaluate the texture field. This is denoted as T theta. So we have two networks, T theta and F theta. For the theta shares a lot of the parameters, as we've seen on the previous slide. So we evaluate the texture hat now at this 3D point p hat to retrieve the color value. And then we simply insert the color value at pixel u. And we can do this for all the pixels to render an image. Now this was easy, but how about the backward pass? How do we backpropagate gradients through this procedure? So what we want to do for the backward pass is we want to first define a loss function. So we use a pretty standard loss function. We have a prediction I hat under the current model, the texture field and the occupancy network. And then we have an observation. So this is how it should look like. Observation I and the prediction I hat. And we simply formulate a loss function by minimizing some reconstruction error, let's say the L1 or L2 loss between these two images. This is going over all pixels U here. Now what we need to do, of course, is we need to compute the gradient of this loss function with respect to the parameters of the network that I've shown before. So the parameters of the texture field and the occupancy network. So this is simply an application of the chain rule. And because both the texture field T as well as the optimal surface location P depend on the parameters theta, I've not explicitly denoted it here, but P hat depends on theta, because if theta changes, also the optimal surface point changes, of course. We apply the rule of total derivatives here. So we have this sum here. Now, these two terms are easy. It's just the derivatives of the texture field, which we can compute using backpropagation. But what about this derivative? The partial derivative of the optimal 3D surface location, so the intersection of this ray with the surface defined by the occupancy network, given the current parameters theta, with respect to the parameters theta themselves. Now, it turns out that this expression has, luckily, an analytic solution. And you can get to that analytic solution by applying the theorem of implicit differentiation to the level set equation. Here you can see the level set equation. This is the function f with parameters theta of this optimal surface point must be equal to the threshold. So if we differentiate now this expression on the left and right hand side, we obtain a closed form solution for this derivative that we are seeking. So I'm not going to go into more details about this, but if you want to learn more about this, then I recommend you to have a look at our recent CVPR paper. Now, what this means is we can now fully analytically and numerically, of course, backpropagate gradients to the parameters of the network. And this is illustrated here. So we have this texture field network T and this occupancy network F. And if we backpropagate gradients to these networks, then we basically can change both the texture representation and the shape representation, as I show here by toggling between these two frames. Basically, in the hope that now, after changing, this becomes closer to the observation. You can see that the shape has changed, but also the texture has become more similar to the observation after this update. Now, the nice thing about this is that we have an analytic solution, and there is no need for storing any intermediate results. If you think about, for instance, voxel-based renderers, differentiable renderers, that where a neural network is used to predict a voxel representation, then you need to store intermediate results at every voxel. And this is not necessary here because we can directly update the surface location. And because of the smoothness properties of neural networks, this propagates very well into the neighborhood, into the 3D volume. So this is just a very nice network, a nice property about these neural networks that we tend to produce smooth results and also backpropagate gradients smoothly, so to speak. Okay, so let's look at some results. So what we have here is an input image. So again, this is a model that's conditioned on an image, a global appearance code extracted from that image. And here are some results. And this is all, like, this is trained with 2D supervision. This is soft rasterizer. This is a result from pixel to mesh, which is trained with full 3D supervision. And this is our results with only 2D supervision. And we can also use 2.5D supervision. So we can, if available, for instance, from an RGBD camera, we can also get, we can also use depth information in this context of this differentiable renderer. So it's not just allowing us to make use of RGB information, but also of depth information. So here you can see some results. Yeah, so let me jump a little bit ahead. So what we also did, what you can see here is, in order to demonstrate that this works on real images, we applied this on a DTU dataset. However, the DTU dataset is not big enough to train a single image prediction model because there's just a small set of scenes. So what we did here is just overfitting to one scene, given all the input images. It's basically doing 3D reconstruction with this implicit representation. And you can see that the reconstructions look quite complete, despite there's a lot of 3D surfaces that are missing in the or invisible from the set of observations that are provided by TTU. Okay, now this is nice, and I want to particularly highlight also one very recent work by the group of Jaren Lippmann et al., where they extended this idea one step further. It's actually concurrent work to ours. And in addition to modeling the color value at every 3D point, model also the material. So they model here now the surface normal and the view direction. They condition on the surface normal and the view direction. And in particular on the DTU dataset, this helps tremendously because the materials are not diffuse. So there's a lot of specularities going on, and this will hurt our DVR model if we don't condition on surface normal and view direction, which we didn't in our paper, but which is a good idea to do. And then another thing we did is, which is easy to do also in our framework, to backpropagate gradients to the camera poses. And turns out that the original DTU camera poses are not very precise. And so you can get much better results if you backpropagate. And you can see this really astonishing results here for the skull, for instance, from this implicit model that's just trained using 2D supervision. Yeah, so another thing I'd like to briefly talk about is training from unposed images. So all of the results that I've previously shown, even the results from this image-based differentiable renderer, assumed the camera poses to be known, at least approximately known, and can only be refined. So we had to run CallMap. Also, Jaren Lippmann's group was running CallMap before to get the approximate camera poses. So can we also learn using these implicit models from unposed images directly? And you have probably seen a recent work on novel view synthesis is called NeRF, representing scenes as neural radiance fields, where they used a slightly different representation than what we did. Instead of representing the occupancy, they represent, using also an implicit function, the view dependent. So they have this view dependency here, RGB color value in the volume plus the density. And then they can apply volume rendering. They basically query this network at all points along the ray in order to render an image, right? So it's a slightly different representation. It's a very nice application of this classical volume rendering approach in computer graphics to these implicit models, right? And the nice thing about this is that now you don't need to constrain yourself to 3D surfaces, but you can also, for instance, model transparency effects or smoke effects, etc. So it's really like modeling densities. So we were using this model. This model was just shown in the context of overfitting, like having 100 or 200 images of one particular scene, like this one that you see here, and overfitting, just training for 12 hours this implicit representation in order to get the best possible reconstructions for novel views. So we wanted to extend this model to the generative case. And this is one work that we have currently under submission, where we try to build a generative adversarial network for this radiance field representation. Now, this is not straightforward because in addition to conditioning now on some latent shape and appearance code, you cannot apply this conditional random fields in a sense that you render an entire image and then, as in classical GAN literature, you compare that image using a 2D discriminator to real images. Because rendering is a very slow operation and it's also very memory intensive. So it's infeasible to render entire images. So what we do instead is we sample rays based on the calibration matrix of the camera and a sampling pattern. So we sample basically a virtual image on a 32 by 32 grid with certain dilation factors. So we randomly sample the scale that corresponds to the dilation factor here, and the location of that pattern in that virtual image. So we get a bunch of rays, and for these rays, we then basically apply this conditional radiance field, this implicit function G that predicts color and density. And then we apply volume rendering to get this predicted patch, but only at the query locations that we have sampled here, right? So only at this, in this case, it's just 5 by 5. And then we do it exactly the same thing. We do the same sampling strategy for real images. And so we query real images at the same locations, right? But of course, these are not paired. This is just a different image. And then we compare these patches using a patch discriminator. And this turns out to work extraordinarily well. So I want to show you some results, and I want to highlight again here that this is results that have been produced, in this case, on synthetically generated data, but where we didn't have access to the pose of the camera. So the pose was unknown. It was just a bunch of 2D images, and the model was able to predict 3D models, a generative model for 3D models, which captures both appearance and shape. So at the bottom, you can see some false color-coded depth maps. On the top, you can see the appearance reconstructions. So here are some novel viewpoints that are generated from this model. You can see also that it captures some of the material properties, and you can change the shape. So it's kind of a hologun, if you're familiar with hologun, but using an implicit representation, and it produces much more consistent results than hologun because it's by definition 3D consistent, while hologun applies additional 2D convolutions, which lead to inconsistency. Okay, so now the last part. I mentioned it before already. These implicit models are really good at reconstructing single objects, but what about larger scenes? And it turns out they don't work so well. So here is a brief overview, like a sketch drawing of such an occupancy network where we have an input X that's encoded in a 1D, in a maybe 128 dimensional feature vector. And these features are then passed to a fully connected network, which takes as input the location P that predicts the occupancy probability for that location. Now, there's a dog barking, so I'm going to close the window. Sorry for that. So now, the problem with this approach is that we have this global latent code here, right? So we condition on one global latent code. So the results, and in addition, we have this MLP, which is not very expressive. So this results in very smooth geometry. So it's only really applicable for single objects. And even these single objects are really smooth, right? They cannot capture fine detail. And because of the fully connected architecture, it also doesn't exploit any translation equivariance, which we like to exploit and which works super well for 2D images and also for 3D convolutions. So we should really exploit it here also, we believe. So if you look at some results of these implicit models for not objects, but more complex scenes, so it's debatable if this is already a complex scene, right? But you can see that they really don't work well. This is now synthetically generated random scenes with a ground plane and random ShapeNet objects on top of them. You can see the reconstruction on the left. This is far from the ground truth on the right. So what we do now, instead of this simple global shape encoding, is we, in our convolutional occupancy networks, what we call convolutional occupancy networks, is we encode the input using a 3D encoder or a set of 2D encoders we can also project on the 2D planes. And then we can apply in this feature volume, this is a coarse feature volume, we apply 3D convolutions as with standard volumetric approaches, but then we query these features using trilinear interpolation at any 3D location in space, right? We can query at any 3D location. And then we put these features input to the fully connected network, basically the same one as here, but it can be more shallow now because we have more powerful features, which also takes the location as input and predicts the occupancy probability. And it turns out that the simple trick helps in scaling these models from simple objects to complex objects and from single objects to entire scenes. So here's some results on single objects. You can see here a point cloud-based input and a voxel-based input, basically super resolution here. The result of occupancy network and the result of the convolutional occupancy network, where you can see much more detail, for instance, on the lamp here. So the advantage compared to the occupancy network is higher accuracy and faster convergence. So we also observed empirically that these models converge much faster when you train them. Here are some results. What we did here is we trained on our synthetic rooms, very simplistic synthetic rooms using this ShapeNet data set put together. And then we evaluated using this synthetically trained network on a real ScanNet data set. From a real Kinect sensor, and it does decently well. And here's a result on the Matterport data set. What we do here is we apply this model that I've just shown in a fully convolutional manner. So we train on synthetic crops as much as fits into memory, and then we apply in a sliding window fashion. We can just apply in a sliding window fashion where each of these windows are overlapping based on the receptive field of this unit that we are using. And thus, this model scales basically to any scene size. Right, so here you can see some results that we obtained with this. Okay, and the last thing I like to point out when going towards more accurate reconstructions and also more accurate appearance is that recently in this paper and also already in the NeRF paper, the authors found that it's actually not ideal to input to this MLP only the 3D location, but what is better for the network, because it has this implicit smoothness bias, is to input an expanded feature representation. For instance, the Fourier features, just expanding these features into a larger dimensional, from 3D to, for instance, 60-dimensional Fourier features, leads to much improved results, as you can see here on the bottom, right? So this is another way and can be combined. It's orthogonal to this idea of convolutional occupancy networks to get good results at high resolution. So this concludes my talk. I want to briefly sum up, and then afterwards I'm happy to take questions, of course. So in summary, I've shown you some recent works on neural implicit representations, which I hope was able to convince you that they are an effective output representation for shape, appearance, material, and motion. And we will see many more applications of these models, for instance, in robotics, I'm pretty sure, in the near future. The advantage of these models is they don't require discretization, and they are able to model arbitrary topologies. And they can be learned from images via differentiable volumetric rendering. And there's many applications such as 3D reconstruction, motion estimation, view synthesis, but also planning, etc., etc. However, because these are implicit models, the geometry must be extracted in a post-processing step. So if you want to go from this implicit model to a mesh, it takes about 1 to 3 seconds for ONet. And extension to 4D, as we've seen, is not straightforward due to the curse of dimensionality. And the fully connected architecture and the global condition lead to heavily oversmooth results that basically just work on simple objects. But there is some promising directions, for instance, using local features like in conv-ONet or PyFu, or more sophisticated input encodings for these MLPs like in NeRF. That's all I had to say. Thank you very much for your attention. And if you're interested, you can also look up our blog. Here's a link to our blog page. So I'm looking forward to any questions you might have.
Cool. Thanks a lot for the fantastic talk. Yeah, very, very interesting, really impressive. Does anybody have some question in Zoom right now?
I have a question. Can you hear me?
Yeah.
Yes. Okay. Hey, Andreas.
Hey.
Nice talk. I have a question. It's about you. In the end, you said there you may see some applications in robotics. Can you elaborate on that? What where do you see the potentials?
So I think one potential application in robotics is, if you have this implicit model. So in robotics, often you don't need a dense representation, right? So if you can predict, first of all, these models are very lightweight, right? So they have a very few parameters, so you can represent them also on easily on mobile devices, where you can use them on mobile devices where, at least at inference time, where you don't have a lot of memory or compute available. And then in robotics, it's often not necessary to get a complete scene representation, but maybe your model using attention or some other mechanisms, or maybe what it has seen in the past, needs to adaptively query, for instance, adaptively query occupancy, adaptively query if there is something at this location. And this is very, very fast, right? You don't need to render the entire 3D space. You don't need to render images. You can just evaluate this very tiny MLP once, and then you query if there's, there's something moving there, if there's something occupied there, what is the semantic category there, etc. So I think that's something that should be useful for robotics, but hasn't been explored that much yet.
Okay, thanks.
Any other questions? I got one, well, more high-level question. I mean, a lot of the work, I mean, including your work and many, many others right now, I mean, much of the proof of concept is done on like ShapeNet-like models, specifically when it comes down to, I don't know, like, some little rendering for separating out material lighting and so on. So what do you think is the main limitation from doing this in the wild? Why can't we just do this on larger scenes, arbitrary images and stuff like that?
Yeah, that's a good question. I think that's kind of the holy grail right now, going to larger scenes. If you go to larger scenes, one problem is at the moment you still need a lot of observations. So first of all, you need these more sophisticated representations that use convolutions, or at least a distributed representation. So it doesn't work if you just use this, like the simple MLP, and try to represent the entire scene. That just doesn't work. So you need to combine it with these more classical methods. And then you still need a lot of images, right? So how, like, for instance, what would be really great, this graph model that I've showed you before, this generative model, is of course only on single objects also, and using, like, a modest, range in focal length and camera distance and camera viewpoints, etc. Right? So scaling this to larger scenes, I think is highly non-trivial, because like the model needs to implicitly learn about the shape, and the shape of the entire world is much more complex than the shape of like this canonical objects. And so you probably need to input some additional knowledge into these models, I would assume, but I don't have a good answer to this, unfortunately.
Well, I mean, scaling it up, right? I mean, we had this one paper at CVPR, like where you do local implicit representations, and you had this paper at I think it was ECCV or so, like convolutional. You talked about it, convolutional occupancy networks. Like basically, you have local MLPs in a grid, or
Right.
local MLPs in some sort of spatial structure, and then you learn how to combine it, but you still have an implicit function. So that seems to me that could be scaled up, at least from a spatial dimension, to a relatively large scene, right?
From a spatial dimension, there's no problem. But like when you say in the wild, I think about not knowing the camera poses, and maybe having only very few images, having noisy images, having images from different cameras, right? So if you look at pipelines like CallMap, it's really sophisticated pipelines with multiple steps that in a very dedicated manner. So implementing, what I meant is basically implementing this sophisticated pipeline like CallMap in a fully end-to-end implicit differentiable way, I think is very hard.
I think I agree with that one, but I would argue, like, my question was not necessarily so far. If in the wild, I meant already, like, basically take the output of CallMap. Let's say you have the camera intrinsics, the camera extrinsics. You have maybe a sparse set of points that but it's still difficult, right? Because like the whole scenery is so complex for large environments. It's more than even like NeRF or so, right? They also show results on a single object with a high quality DSLR, very, like I feel like we're missing still something as a community there to, I don't know, is it like a data question? Do we need more data sets? Is it more a question of we need still better representations and so on?
Mm-hmm. Yeah. I mean, so for instance, like I don't think it's there's also a paper by Christian Theobald's group on scaling this NeRF model to larger scenes, where they basically also use a distributed representation, and they get very good results and it scales up well. But there is some difficult questions to be answered. So for instance, what is difficult for this radiance field model is if you have objects that are very close and objects that at the same time are very far. So for instance, if you look at a kitty scene, you typically see like this car 2 meters in front of you, but then maybe you see like 300 meters down the road. And so if you want to render this, it's very difficult, right? Because you need to render like close cars very precisely and objects that are very far, efficiently, because you can't investigate like these millions of samples along this 300-meter long ray.
No.
And so I think there's some work to be done here. Yeah.
No. Yeah, I agree. Any other questions? Anybody else on Zoom? I mean, we have a lot of questions on YouTube. Actually, I can go over these ones too.
Yeah, I have one more question. It's not a really question, but so there is NeRF in the wild. So it's a project from Google, and that's because you guys were just talking about using these methods in the wild, and I think that's one example which also produces nice results. It seems like they mainly use buildings, and it seems also like that the photo collection is mainly crowdsourced. So I guess they, can't maintain like the same quality, so the quality varies.
Yeah, that's a good point. Yeah.
Looks.
So it's a nice. So what they do in this paper is a nice step, right? So they basically, if you do it in the wild, you have to also think about other effects. Like if you have multiple different cameras, then you need to, like, first of all, there might be the scene might not be static. There might be people moving around, so you need to separate the dynamics from the statics and so on. So that they did pretty nicely in that paper. Yeah. Yeah, it's a good point. Yeah, it's in the wild in terms of the cameras, but I think we also require call map and like good post initialization. If I have it right on top of my head, it's mostly about like separating these different appearances based on daytime and also the dynamic objects. And this is already a great challenge, and they did a nice job in that paper. Yeah.
Any other questions?
Yes, I have a question, if it's possible.
Sure.
Thanks. It was a nice talk, and I really like your research blog. So my question is basically, how much photorealism do you think that it will be necessary in order to improve the representation, the understanding of the scenes? This is more related to this work that your group did about joint estimation of pose, geometry, and the material. So I was curious, how much like a photorealism it will be necessary to improve the representation.
Are you talking in terms of the ground truth, or in terms of the model, or?
Yeah, what I mean is like the examples are mostly with synthetic scenes, but then when you go with real scenes, you can have like a very complex effects.
Yeah, so that's hard. So first of all, what you encounter in terms of materials and yeah, in the real world can be really, really challenging, right? And it's not like something that you would easily replicate with synthetic data sets. And so it's important to look at the real world. And then I think there's a difference in, if you do something like NeRF or graph or NeRF in the wild, the modeling like view dependent light variation, that's relatively feasible, but this doesn't allow you to change the materials or the lighting, right? So it doesn't completely disentangle the lighting. You cannot completely disentangle geometry from lighting and materials. And that's something that at least I and my group like to do, where you basically take images in the wild or close to in the wild, and produce a representation that could be used in terms of a simulator, right? So you generate basically a real world simulator that you can modify, where you can modify the light sources, where you can modify the objects, and it still looks photorealistic. That would be great to have, I think.
Okay, any other questions?
Okay, thanks.
I have one from YouTube. So it's actually an interesting question. So let's say we had a lot of resources. What data sets are we potentially missing in order to get better results? What's the limiting on the data set side?
Mm-hmm. Yeah, so I think what is like the material aspect is really difficult. So we see some exciting progress now in the material domain, but mostly using synthetic data sets with some hand-engineered materials and capturing materials in the wild, like really the material, the BRDF properties, is really difficult. So there's all kinds of capturing devices that work like in the laboratory, like gantries or even like texture capture devices, which you can put on the wall and it captures the texture. But there's not really something that works like for all types of scenes and works very well. And so I think this is what is probably mostly missing, like really good data sets that have also these material properties. And then the next thing that's missing, but there is a lot of data sets, and that is data sets with very good geometry, right? So I think these data sets like Matterport or Scannet, they are great, but if you walk through these reconstructions and you would just reproject the appearance, even if it would have materials, just by the errors in the reconstructions, it's not precise enough. So I think having a better, having a better geometry, and then for outdoor, it's even more challenging. Outdoor, you cannot use these dense structured light sensors, but you need to deploy some sparse LiDAR points. Then a lot of these data sets are proprietary because the companies don't want to give them away. Yeah, so I think that's mostly missing, because if you have the materials and the geometry, then from the images you can do, or if you know something about the materials and the geometry, then from the images you can basically do the rest. You just need to capture a lot of images, and that's relatively cheap.
I mean, lighting is the same, right? Like it's very difficult to get ground truth annotations there.
Yeah, lighting also. Yeah.
There's actually, this open surface work from Kavita Ballas and Noah Snavely's group. So these guys, they annotated, is it the same material?
Yeah.
Do you think that's enough?
I don't think so, but I don't want to make a strong point here.
Sorry, can I ask something related to the last question? When you say that there is not data sets for the material, you mean like you have joined, you have the light, the material, or the geometry? Because I think there is this bond data set, and there is this Benzel. I think they have a material, capture with this device. So what do you mean when you say that there is not data set for the material?
Yeah, like for materials more in the wild, there is material databases, but they are pretty old and small, and so the Merle database, for instance, right? So many people still use the Merle database actually, and there's better databases now, but the progress I feel is slow. And we need to make more progress and faster progress, and we need to have materials in the wild. So I need to basically go outside with my car and capture a scene and know the materials for the scene, and I need to go indoors for instance Matterport, right? If I would have the materials for all surfaces in Matterport, that would be great. Yeah.
Basically, you want to have a light stage everywhere, but it's just very hard to scale it up to some, I don't know, like Kitty with light stage data would be great at every position for every car at every time, right? But it's obviously not practical. Yeah,
because if you, with neural networks, like you can always put a 2D convolutional neural network at the end of your, to map from something that's close to photorealistic to something that's photorealistic. But that doesn't mean that it captures, really disentangles all the underlying properties, so that when you manipulate the scene, then the objects basically are properly disentangled. That's also what we for instance, what we found with Hologun, right? Because Hologun actually only produces like really good looking images because it has this additional 3D and 2D convolutions at the end. But what happens then, what we did, for instance, is we applied the output of the Hologun model, like when we render images from Hologun for different viewpoints, and then we apply call map on top of that. That doesn't work at all because the images are not consistent. You cannot reconstruct the geometry from that again, right? So that's, yeah, so disentangling these aspects and getting access to them, I think is really crucial.
Yeah, I get one last question. There's a bit of a discussion right now on YouTube, right? Basically, can you do all of this on synthetic data? You know, we just simulate it, see how it goes. Can we transfer it? Is that doable? Is that the way to go then?
So I had in my group just 1 week ago, Manmohan Chandraker giving a talk, and I was really like the group at USCD. Also the group of Ramamurthy et al. They do really amazing work in the space of creating huge amount of data with materials and then transferring this to the real world, and it works amazingly well. So if you would have told me that 5 years ago, I wouldn't have believed it. So it seems like as you can use, you know, flying chairs to pre-train your optical flow model, you can use these flying blobs to pre-train your material model. However, I think there are still some questions to be answered. So it's not always clear how accurate these reconstructions are, because precisely for the real world, we don't know exactly the ground truth for these properties. So, but I think like also one thing that I'm a little bit yeah, that's a little bit sad, is that in the graphics community seems to lag a little bit behind the vision community in terms of openness of code and data sets. And so a lot of the work that is potentially interesting and relevant in this area has no published code or data sets, right? And so these material databases and object databases are not really publicly available. For I think there's one paper now very recently that will make a large scale data set like this available, and I'm looking very. It's also from Manmohan. I'm looking very much forward to this.
Yeah, I agree. It's challenging. There's not a lot of data available. I mean, yeah, I mean, it costs a lot of effort to create it, and then most of the companies are behind it, right? And they want to protect their value and so on.
Probably, yeah.
So, I mean, it's interesting. Okay, all right. We're already a little bit over. Thanks so much. I'm really sorry that it took a little longer, but it was really exciting. We probably could have gone on for still a while, but it was really great to have you. Yeah, thanks a lot. So,
thanks for having me.
Thanks.
Have a good weekend. Bye-bye.
Yeah. See you. Bye-bye.